we're recording. Oh, and everybody's here. What's up?
You've got them displayed.
You've been displayed. All right, welcome everybody. Perfect timing. Are you sure you want us to find properly? So today we are going to take some of the stuff you learned last week about rings of integers and go on a little factorization journey, learn a bunch of theorems, do some cool examples. It's going to be a lot of fun. In general, the goal is to kind of characterize rings with bad factorization, or essentially rings that aren't UFD. That's what we're going to be mainly talking about today. So in order to do that, let's recall some of our definitions of what a UFD is from way back in the beginning of this class. So most of the time today, ours will be an atomic domain. We have the following equivalent characterization. So kind of the first and most direct definition of UFD is given any two irreducible factorizations. These are irreducible factorizations. Then what? We know n equals m, and there exists some permutation of the elements of n such that alpha I is equal to beta sigma I times some unit ui. So this is maybe not the nicest way to define UFD, but it might be the clearest. Can somebody give me another equivalent definition of a unique factorization domain?
Every non-zero prime has a non-zero prime element.
Every non-zero prime ideal, right? This is Plansky, right?
We don't even need to assume atomic for the.
We do need some heavy duty stuff, but right, every non-zero prime ideal contains a non-zero prime element. This is really nice because now we have an ideal theoretic conception for our theorem. And this is also kind of the cheater way that you show that a PID is a UFD really, really easily. One more we can state even quicker probably.
Every element factors into prime.
Right. Every element has every non-zero non-unit has a prime factorization. So if something satisfies one, hence all of these, we're going to call it a unique factorization domain. And this is essentially the gold standard of factorization. Yeah.
Using the third one, we're gonna have a fourth one saying that every irreducible is prime.
Yes, that would be the same, right? Every irreducible is prime would be equivalent because then every non-zero non-unit can be factored into irreducibles and thus into primes, and the other direction is also not hard. So yeah, that is equivalent. In general, primes are always irreducible. Irreducibles aren't always prime. Showing primes are irreducible follows pretty quickly from just the definitions. But yeah, good point. Another one. There are a lot, and I'll talk about at least one more before the end of today. But of course, atomic domains aren't unique factorization domains. In general, we've seen a lot of examples where this doesn't happen. The classic, 2 times 3 is 1 plus square root of -5 times 1 minus square root of -5, and a bunch of other examples. So today we're going to develop some ways of characterizing basically how bad factorization is, or how far away we can get from this, which is what motivates the following definition. So once again, R is going to be an atomic domain. Then we're going to call R a half factorial domain, which from now on I'll refer to as an HFD. If alpha 1 n equals beta 1 beta m, where these are all irreducibles, of course. Implies n equals m. So essentially, what a half factorial domain is a domain where any two equal irreducible factorizations have to have the same length. So what's probably immediately clear should be that any UFD is an HFD, right? We get that immediately. We can also see that from the uniqueness, right? Unfortunately, there aren't as many super nice characterizations of this as there are of this. A natural first question, of course, would be, is this actually distinct from this? Which is a good question to ask anytime you have a new definition. And I would say, a priori, it is not entirely clear, if you've never seen this definition before, that there are domains which satisfy this, but do not satisfy UFD. To motivate that a little bit, there's a definition that we kind of missed here. I'm sure there are a lot. Pedro gave us another one. We can actually relax number 1. Anybody know how? We can actually assume this. This is actually all we need to show UFD. All we need to show is that if you're given two irreducible factorizations in the same length, then they are unique up to multiplication and reorder, 5 units and reordering. So you don't even need this condition. So it's kind of a relaxation of the having the same length. And this is a relaxation of kind of the second condition. So it seems plausible that if this is all we need, maybe we can relax this, and this is going to be sufficient as well. But it turns out that is not the case. There are half factorial domains that are not unique factorization domains. And unfortunately, as I am not the supreme, Order of Merlin first class factorization warlock that Dr. Kuykendall is, I'm not just going to ask you for an example and have to verify it on the spot. I'll just give you a couple examples and we'll talk about it. All right, so I can clearly see why this is not a unique factorization domain. Can anybody tell me a quick reason?
The clause is plus xc, right?
So it's oh, sorry. Yes, thank you. This could, of course, that would be problematic. Yeah. Any takers? Well, what is the consequence of being a UFD? What is one important constant? Any UFD is also what?
Yeah.
No, other way around.
Other way around.
Right. Think about, sorry. A property that is really nice in rings. Integrally closed. Any UFD is integrally closed. This ring is not integrally closed. And I can tell why. I is not in here. But I is integral over this ring. So it's not integrally closed.
No, I am integral.
So not integrally closed. So this implies non-UFD. All right. Now, the fact that this is an HFD follows from the fact that irreducibles in this ring are of the form x half of x. Now, you can convince yourself of this by noting that if x doesn't factor out, because this is a power series ring, you're going to get a unit. So the non-units look like x to the n times f of x, and the irreducibles are going to be the ones of power 1. So you can take some time to maybe mess around with this, and the consequence is going to be, take any non-zero non-unit, you can count the number of irreducibles in any factorization as the number of x's that you can pull out. Now, this is generally a good way to show that a ring is not UFD, showing not integrally closed is pretty fast a lot of the time, but we don't have that in general, right? There's an enormous important class of rings that are integrally closed, but typically aren't UFDs in general. And that would be Dedekind domains, right? Or in particular rings of integers. So this ring is integrally closed and an HFD. Yeah.
I have a question. This f in 0 should not be 0, right? This f in 0 should not be 0, right?
It's okay because like we're assuming that this is some g of x where the constant term is not 0, essentially, is what we're assuming, right? We're assuming we can factor an x out, right?
Sorry.
So I'm just saying the irreducibles are going to be elements where that constant is 0, because otherwise there'll be a unit, which is essentially saying you can factor an x out, right? So right, g of 0 won't be 0.
Yeah, but I was asking about f because, for example, if s is x squared is not irreducible.
Oh, I'm sorry.
Next to the K.
Sorry. Here, maybe I can make this a bit clearer. The non-units are going to be of the form like that, this, right? And then the irreducibles are going to be the ones where you have x times f of x, where f of 0 is
right,
a unit, right? Thank you. Exactly. So back to this one. This ring is, of course, integrally closed. It's a ring of integers, but it turns out it is also an HFD. The reason why we'll be seeing later, you know, this famous factorization, which I already alluded to earlier, shows that this ring is not a UFD. We'll see later why it is in fact an HFD. But it, of course, is integrally closed. And you could show that these are irreducible factorizations just by looking at the norm. So what we would like to do in general is find a way to characterize those HFDs that are not UFDs. But of course, this is hard to do in general. There's no nice conception that we know of to say, here's a test to determine whether that this is a HFD that's not a UFD. However, it turns out that for rings of integers, we do have just such a conception. So I'm going to clear all of this and hopefully it erases what I want to talk is too good. theorem over the exact same stuff. This is
It's not a five-star high warlock of transitions.
true, true. So this is a theorem due to Carlitz from a paper in 1960. This paper is like a page and a half. We're essentially going to do the whole paper here today. But now, for now on, most of the time, R is going to be a ring of integers. The R would be a ring of integers. Then R is an HFD if and only if the order of the class group of R is less than or equal to 2. So this is the first example of the class group serving as a measure of failure of unique factorization. We'll talk about this even more going forward. But the really nice thing about this is it gives us an exact characterization of which HFDs are UFDs and which HFDs are not. Anyone in particular, how does this tell us that?
Exactly two. Then it's not a UFD because then we have non-principal ideals or dimension one.
Right, exactly. For Dedekind domains, you have UFD if and only if class number 1. PID and UFD are the same here. Exactly, the rings of integers of class number 2 are going to be the exact rings that are HFDs but are not UFDs, which is a really, really nice characterization. And we are gonna prove this because it gives us a lot of intuition into how we can manage elements in the class group and what they kind of look like. So we're going to leverage a couple things in this proof. Namely, any ring of integers is a Dedekind domain, which is essentially the best we can do after UFD, in the sense that we no longer have unique factorization of elements, but we have unique factorization of ideals. And the theme is going to be, well, I don't know how an element factors, it doesn't factor uniquely, but I can look at the ideal generated by that element and how that ideal factors, and that'll actually tell me a lot about how the element itself factors. And we'll use the class group to suss that out. And then the other thing, why do I assume that it's a ring of integers, or why did Carlitz assume this instead of just a Dedekind domain? Well, last week you talked about a characteristic of rings of integers, very important characteristic, which is that every ideal class contains a prime. In particular, in this case, infinitely many primes. And actually even more than that is true. They're in the limit, they're actually uniformly distributed among the classes. But all we really are going to need is that there is a prime ideal in each class. And that's why we make this assumption, but the same will hold for any Dedekind domain for which that's true. So let's start in the reverse direction because it's a little bit easier. So I'm going to refer to the order of the class group as H, which is kind of typical notation. And we'll assume that in this direction, H is less than or equal to 2. Well, we kind of already talked about this. H equals 1. R is a PID, implies UFD, which implies HFD, and we're of course done. So we're going to assume that H is equal to 2. And we're going to let X be a non-prime irreducible. In all. Okay. Let's now consider the factorization of set of the ideals generated by this element into prime ideals. So first, we're gonna note that R is greater than or equal to 2. Why is that? Sorry, because it's hard to read. Try to erase a little bit better.
It's not prime.
Right, it's not prime. If R was 1, then it would generate a prime ideal, but it's not prime. So it can't do that, because if an element generates a prime ideal, it is itself prime. I claim that R is actually equal to 2. And so we'll assume not, and show that we can derive a contradiction. Right, so we'll assume it's greater than 2, which if we can contradict that with this condition, will be sufficient to show that it's actually equal to 2. Goodness. All right, so we know it's at least 2, and we know that none of these primes can themselves be principal. Because if any of these primes were principal, then there'd be a prime element dividing x, but x is irreducible. So if a prime divides an irreducible, well, it's equal to that prime. So none of these are principal, but because h is equal to 2, what do we know about P1, P2? It's principal, right? It's the class group is isomorphic to Z2. So we're essentially taking 2 non-zero elements in that group, and when you multiply any two non-zero elements, you'll get 0, or essentially you will get an element in the set of principal ideals. So I'll just call that the principal ideal generated by alpha. So x is equal to, the ideal generated by x is equal to the ideal generated by alpha 3 up to er. But this is principal and this is principal, so this also has to be principal, right? Otherwise, we would get a contradiction. So let's call this beta. But then the ideal generated by x is equal to the ideal generated by alpha times beta, which implies that x equals alpha times beta times u for some unit. This is of course a contradiction of the fact that x is irreducible. These are both non-zero non-units because of the prime factorization. Any questions on that? So we've shown that any non-zero non-unit factors into exactly 2 primes here. So now we're going to take two equal irreducible factorizations. And we can assume without loss of generality that none of these are prime. Why can we do that? Our goal is to show that any irreducible factorizations have the same length. Why can I just assume without loss of generality that none of them are prime? Exactly, right? If alpha 1 was prime, well, has to divide one of these irreducibles. Well, then it has to equal one of these irreducibles. So it's on both sides. We can divide it out. We then decrease n and m by 1. Well, if we can show n minus 1 equals n minus 1, we can show n that's the same. So we can assume they're non-prime. And we just showed that as ideals, these principal ideals are all generated by 2 primes. So we'll let P, well, let me write this maybe a better way. let the ideal generated by alpha I be bi1, bi2, the ideal generated by beta j equal to j1, j2. Then, if I just basically take ideals on both sides, what I get is that P11, P2, and does anybody want to take us home?
This is the again, we're done.
Sorry?
This is the account, we're done.
Right, because prime factorizations are unique. That it can 2n equals 2m. I don't want to write the statement quite yet. All right, we'll go in the other direction now by contraposition. So we're going to assume, yeah,
You have the backwards arrow twice.
thank you. My brain was thinking contraposition,
Yeah.
flipping it around in my brain. Yes, thank you. So we're going to assume that the order of the class group is strictly greater than 2. We're going to show that it's, in this case, not an HFD, and that'll be what we want. So we're going to break this down into 2 cases. Case 1 is going to be that there exists some element in the class group with order n greater than 2. This is going to be our first case. So we'll call that element the ideal class containing I. And now here's where we're going to use the fact that every ideal class contains a prime ideal. So I'm going to just arbitrarily let P be in this ideal class, and I'm going to assume it's prime. All right. And we're also going to choose Q to be in the inverse class, also prime. Okay. So why would I do such a thing? Well, I claim that the ideals P to the n, Q to the n, and PQ are principal and generated by irreducibles. So the fact that they're all principal follows directly from the choices that I made. P to the n, well, that's the identity. And in terms of classes, the principal class. Well, the inverse class is the same order, so Q to the n, and these were inverses, which means precisely that their product should be principal ideal. Now, the fact that they're irreducible takes a little bit more work. So we've established that they should be principal. Now we'll assume that alpha equals AB. And we want to show one of these is a unit, right? Well, then by the uniqueness of the prime factorization, we get this, of course. Now, why can I make this claim that the ideal generated by alpha has to be p to the k where k is 0 or n? Of course, it has to be k less than or equal to n, but why are these our only options?
The order of the classes.
Right, the order of this element as a class, this element's class is n, right? So for any k less than n, this won't end up being principal, right? Except for 0, in which case this is r, and so this is a unit, right? So because this is all symmetric, either this is 0 for A and n for B, or vice versa. I can say without loss of generality that k is 0, which implies that alpha, the ideal generated by alpha is R, which implies that alpha is a unit.
I think alpha there should be a.
Yes, definitely. Alpha being a unit would be a problem. Yeah, of course. And this is really all that I'm going to erase the statement now to be a bit more contiguous. So to show that this is generated by irreducible is very similar. So now we're going to consider following factorizations: p to the n, q to the n. Right. And I'm going to choose irreducibles so that p to the n alpha q to the n equals beta and pq equals gamma. Thus, so just turning these to principal ideals that they generate. This implies, of course, this is alpha, beta, and this is the ideal generated by gamma to the n. This implies that there's some unit such that alpha times beta equals u times gamma to the n. And we assume n is greater than 2. Oh, well, that is true. All right, so I would like to get through a bit more than this, so I'm gonna leave this other case as an exercise, but that's gonna be the case where every element has order 2. And you're gonna use the fact that it has a Klein 4 subgroup and do a very similar kind of argumentation to get it, but I don't want to spend the rest of the class doing that. Any questions about the proof though?
Why use a unit here?
Right, because alpha times beta doesn't necessarily equal gamma to the n.
Yeah, but why is not something else? That's not a unit.
How do I know that it is a unit?
Uh-huh.
Because they generate the same
Okay.
ideal.
Yeah. Yeah, true. Sorry.
Right. Good question. Any other questions?
Let's work.
All right, so this is essentially our first foray into characterizing rings that aren't unique factorization domain. And we can do this even more generally than HFD. It's going to turn out that HFD is really the best case outside of UF. So once again, we're gonna let R be an atomic domain. And we define the elasticity of of a non-zero non-unit are as follows. So typically, we're going to use rho of R to denote the supremum of the ratios n over m such that R equals so this definition is essentially saying what's the largest ratio of lengths of irreducible factorizations of the given element. So this is a measure of how bad things get, essentially, right? The higher the elasticity, kind of the worse things are, because you can get factorizations very disparate lengths. Now, what can we say immediately? If R is an HFD, if and only if
One.
right, elasticity is 1. All factorizations have the same length. And we can define this for a domain. We say the elasticity of the domain itself is very similarly the supremum of n over m, except we're not taking a particular R anymore, just when you have two equivalent irreducible factorizations of length n and m, right? So this is going to be a lower bound for this. And it turns out that you can get some pretty funky things happening. You can find some pathological examples where elasticity ends up being infinite or irrational or all these things because of the supremum, by, of course, looking at some cleverly constructed polynomial rings, cleverly modding out the requisite ideals, but we're not going to look at any of those today. Yeah. I want to consider, however, this and this element. So in general, when I'm looking at quadratic rings of integers, what's a good way to determine if an element is actually irreducible or not? Yeah, look at its norms. The norms here, because thank goodness I chose a imaginary quadratic. They're all nice and easy, kind of, because they're all positive. So we can clearly see that this has no solution. This is number 2 or 3, right? So the norm of 2 here is 4, the norm of 3 is 9. So any proper divisor would have to have norms 2 or 3, which is impossible. So 2 and 3 are irreducible. Similarly, the norm of this element is 18. And by inspection, we can find that the only elements of norm 18 are going to be these ones, and they don't properly divide each other. They don't divide each other. So believe me, these are in fact irreducible factorizations. So what does this imply? This implies that the elasticity of the ring is at least 3 halves, right? In particular, the elasticity of alpha is at least 3 halves, which implies that the elasticity of the ring is at least 3 halves. Does anybody know, in fact, the elasticity of this ring Does anybody know?
3 has.
No. It is two. And I was hoping that we'd be able to get to see exactly why that is, but I don't know if we're gonna quite get there. But if we rush, we might get to the statement. There's actually a example in here that I bet you've seen in this class that you can show you achieve at least elasticity of 2. All right. Pretty good on this. And a little speed around here. So, in order to talk about elasticity in rings of integers, I need to define I need to give you a purely combinatorial definition. We're gonna do a little bit of ring theory. Everybody's favorite algebraic object. We're gonna let G be a finite abelian group. We call a sequence G1, Gn of not necessarily distinct elements of G, a G sequence. So essentially, a G sequence is a multi-set of elements of G. We say a G sequence G1 through Gn is a 0 sequence if the sum of the elements is equal to 0. This is the identity of the group written additively. We in groups, we like to write them additively. All right, so pretty straightforward there. But that leads us to the following. Very useful definition. Once again, G, a finite abelian group. No, absolutely not. The Davenport constant of G denoted D of G is defined as follows. So there's actually 2 equivalent definitions of Davenport constant. So we can call it the minimum n such that any G sequence of length n has a proper 0 subsequence. We're running out of room here. So essentially, take an arbitrary sequence here, has to have a proper 0 subsequence, or equivalently, we have a maximum characterization, maximum n such that there exists a G sequence, say 0 sequence. Of length n with no proper 0 subsequence. So let's look at some examples. Sorry, that got a little bit cramped. So this is an example of a G sequence in particular, a zero sequence in Z2. If I add these up, I get 0 in Z2. But this also has a proper zero subsequence. Because we have 0 essentially in here, right? So this would not fit, this characterization here, because it's a zero sequence, but it has a proper zero subsequence. So this doesn't imply that the Davenport constant is greater than or equal to 3. But this implies it's greater than or equal to 2, because I have zero sequence with no proper zero subsequence of length 2, right? So the nice thing about these dual characterizations, and you can show pretty easily that they're the same, is that one is good for showing upper bounds, one is good for showing lower bounds, and you have this kind of min-max different definitions. So I want the Davenport constant of Z3. Turns out that this is 3. So what's the quickest way to see this? Well, let's try to construct the longest sequence we can with no proper zero subsequence. Okay. So we can't start with 0. And 1 and 2 are isomorphic here, so it doesn't really matter which we start with. So I'll start with 1. Now I can't add 0 once again, because I would just have a zero subsequence. And I can't add 2 now, so my only other option is 1. All right. And the same thing would happen if I start with 2. Now I have no choice. I can add 1 or 2 or 0. I'll get a proper zero subsequence. So 3 is going to be the length of the longest zero sequence with no proper zero subsequence. Now you may ask yourself, is it the case that D of G is always the order of the group? Answer is no. And as an example, we look at the Klein 4 group. The Davenport constant of this is anybody? 3. Yeah. Of course, is strictly less than the order of the group. Now you can see that because every element is its own inverse, right? So start with you can't have 0 either. Start with 1 0, but you can add 1 0, add 0 1 per se. Now the only option is one of those, which would give you a zero subsequence, 0, which would give you a zero subsequence, or the other element, and then that whole sum would be 0. So 3 is the best you can do. Turns out that the Davenport constant, and this is what I'll end with, is going to be finite in general. Anybody know or want to guess?
Size of the group at least, would probably do better.
The Davenport constant is bounded above by the order of the group. And this example shows that this is sharp upper bound, but it's not achieved in general. But immediately we get a corollary, which is that for cyclic groups, D of G equals G, because you can always construct the sequence of n copies of the cyclic generator, right? So that would give you a zero sequence with no proper zero sequence at this length, which would show the other direction. And actually, I think on the converse is actually true, that this is achieved if and only if a group is cyclic, which I believe I'm the first one to ever say explicitly. But now the proof of this is very, very cool. It's a neat little combinatorial trick that I was hoping to do, but we're not going to have time. So just as a preview for what I'm guessing Dr. Quickendale will talk about after break, all this stuff seems a little bit random, but what does this have to do with factorization? Well, it turns out that this combinatorial constant related to the class group of a ring of integers determines the elasticity of that ring. But I will leave that for next time. Are there any questions about what I've talked about today? I was a little bit ambitious, I think, in what I was gonna get through, as is often the case. Do a little number theory, yeah,
When we proved Carlet's theorem,
Yeah.
it seemed like in the first half, we didn't really use special properties about rings of integers.
yes.
So that holds in that direction.
Yeah.
In general. and-
Good question. I was gonna talk about this with, when we talk about elasticity more generally for rings of integers, but yes, you just need a Dedekind in one of those directions. It's the other direction that requires, at least one prime ideal in every. And this is, of course, this does happen in other rings that aren't rings of integers, but that's what people don't really care. But yeah, good question. The direction.
We actually need infinitely many when we deal with the situation where we might have, like, only elements of order 2. Infinitely many primes in each class, because we need to be able to, at least 2, I guess, because we need to be able to choose different primes for the part we didn't get to.
No, not necessarily,
So we really just need, At
because,
least
you just need, because you're choosing them from distinct classes.
for the case that we didn't do where, we have only elements of order, 2.
Right, so you would essentially choose P in one ideal class, Q in another ideal class. Because we can show that it has Z2 as a subgroup, and K in here. Why would I need infinitely many primes?
I thought you might need to choose a different prime in the same class.
Because what I do here, if I look at this factorization.
Okay.
Because, and here's the thing with the Davenport constant, this forms a minimal zero sequence, this does, and this does. That's why they all generate irreducibles, and this will be 1, 2, 3 irreducibles, but this will have 2. But I only needed 1 from each class.
So this theorem really will hold as long as we have, 1 prime in each.
Yeah, typically a lot of the time you only need 1. Same for the theorem we'll talk about next time, but in this case, we actually get way more than that. Yeah, any other questions? I'm really hoping to get into how you calculate the class group of a ring of integers, but perhaps another time. Thank you guys for your attention and have a good break.
There